Hi, I'm Austin. I did my project on calculus with knot polynomials. So first I'm going to go over what basically knot theory is. So it started in like the 1850s when physical mathematician Lord Kelvin started experimenting with knots. And this was because he had a theory that each atom had its own specific knot, each element rather, and that all atoms were knots in the ether. And what the ether was essentially was an antique idea of air. And that was his theory. And this is when knot theory started to be extensively classified. And mathematicians started collecting knots for each different element. And as time went on, they realized that this theory was incorrect, or probably incorrect. And they discovered some other interesting applications. And among those applications are DNA and solar flares. And the reason why DNA has application is because so much information is compressed in such a tiny space, the nucleus of the cell, that oftentimes the DNA gets knotted and twisted and stuff. And I was going to look into that. I was going to see if there was any relationship between the types of knots, the complexity of the knots, and if there are any mutations or cell deaths, but it didn't work out. And the other interesting application is solar flares. And apparently solar flares form knots on the sun's surface. Sometimes they go like this. And the reason that is it's based on the magnetic field of the sun, and it's actually very complex. I was also going to do that, but it was beyond my grasp. And I need to tell you the difference between what you would consider a knot and what a mathematician considers a knot. So the one up there on the left, you would call a knot, but it's not a knot according to mathematicians because it's not a closed loop. So if you were to attach the two ends of that knot together, then you would have a knot as mathematicians consider it. And that's that one on the right is a knot according to mathematicians. And so something that knot theorists do is they try to figure out if any knot can be simplified into a simpler version. And so what's interesting about this knot right here, if you can imagine holding that knot in your hand, you would actually physically be able to untwist it and get just back to an original circular loop. And that circular loop is called the unknot. And by the way, that knot right there was created by a knot theorist with the coolest name ever. His name is Morwen Thistlethwaite. And no, he does not have a lisp. And yeah, so there are different ways the mathematicians get between these two projections. And there are planar isotopy and Reidemeister moves. And what planar isotopy basically is you just warp the knot. It doesn't change the knot at all. You're just rearranging it, essentially, as you can see on top. And then there are three Reidemeister moves that you use to rearrange knots. Type 1, Type 2, Type 3. And it was proved in 1926 by the German mathematician Kurt Reidemeister that those don't change the knot. And so that is a guaranteed way to find simpler projections. And so all of you should be familiar with this. Hands up if you are. Everybody, yeah. And what's interesting is actually, if you start with this, that's a very simple projection of your headphones. And if you do the Reidemeister moves enough, you could actually create that mess right there. That's sort of a real-life application of knot theory, sort of. And so mathematicians have been tabulating knots for a long time. And right now they have something like 1 million knots tabulated. But they don't have them tabulated for sure because there are a lot of repeats. And it's very difficult to tell if any two knots are the same because they have all these moves and all these crossings, and it's really complex. And so they developed these things called invariants that don't change between projections of the same knot. And the two examples I have are tricolorability and linking number. And tricolorability is exactly what it sounds like. It's just the ability of a knot to be colored 3 colors without the same color meeting at a crossing. So you can see the knot up there, the trefoil knot, as it's called, is tricolorable. And the linking number is you assign a direction on the knot. And based on whether it's going like this and this, or this and this, you assign the plus sign or a negative sign. And so that knot right there has 6 pluses and 2 negatives. 6 minus 2 is 4. And then you divide it by 2 to get the linking number, which is 2. And so what I looked into is the environment that mathematicians use called the polynomial. And these are derived in several different ways. And there are several different polynomials. The most popular ones are the Alexander, the Jones, the Brackett, and the Homfly. Homfly is an acronym. And this is a basic derivation of how you get the bracket polynomial. That is a terribly drawn trefoil knot. So what you do to start with is you choose one of the crossings. In this case, I chose that one. And you change it to this, and then you change it to this. You multiply 1 by a, you multiply 1 by a to the negative 1. And then you keep simplifying down until you have only unknots in the brackets. And so the bracket polynomial that you get is a plus 1 plus a to the negative 2. And so I had two different questions that I tried to answer with my investigation. And the first one was that I collected all the polynomials for the 14 simplest knots, and I derived and integrated each of them. And I tried to see if there are any relationships between them and the characteristics of the knots they represent. Those are some examples up there of some I did. I used Wolfram Alpha because Wolfram Alpha is everybody's friend. And I did find one pattern. And essentially what I found is for every derivative of an Alexander knot polynomial, another polynomial of a knot has similar complexity at the same polynomial multiplied by an integer must have a negative 1. That sounds like a bunch of mumbo jumbo, because it is. But essentially what I did is I found that when you derive the polynomial, another knot had the same polynomial multiplied by a negative 1. And I wasn't able to go any further with this because I actually just discovered it like a few days before I finished my paper. But I think future research into this might be interesting if there's a relationship between the two knots when you multiply by a negative 1. And also if you multiply by a different number, what that number means for the two knots. There's some examples up there. Again, further research would be necessary. I think it would be pretty interesting. And so the second question I tried to answer was with re-representing polynomials so they only have positive exponents. And the way to do that is with Taylor series. And if you've taken calculus, you know what a Taylor series is. But I'm going to explain it anyway, so don't worry about it. So the thing is that traditional polynomials only have positive exponents, but most knot polynomials have negative exponents as well. And so what a Taylor series is, it's an infinite sum of terms that only use addition, subtraction, multiplication, and division. And that is the formula right there. All this means is that you're adding up forever the nth derivative of x sub 0. X sub 0 is just where you're centering it. It's just going to be 0. And you're going to do that forever and until infinity, and you're going to add it together. And what's interesting is that calculators actually need to use Taylor series, because calculators don't know what sine of x is, or cosine of x, or natural log. So mathematicians actually find what the Taylor series is for those things, and calculators actually use approximations. And so when you type sine of x into your calculator, it's actually doing x minus x to the third over 3 factorial and so on. And so here's an example of something I did. It looks awful, but I'm going to explain it. Hold on. I started with the original polynomial. And I substituted in t plus 1 for x. And the reason I did that is because it ends up being much simpler. If you want to know why, you can just ask later. I don't really have time. And it's not very important. And then you see right there 1 over t plus 1 squared. I substituted the infinite series for that, which is 1 minus 2 plus 3t squared plus 4t to the third. And then I substituted the 1 in for 1 over t plus 1, which is 1 minus t plus t squared minus t third, and so on. And I simplified it down to that. And so I'm just basically rewriting it. And then I did it again. And this is something my mentor suggested, is that I integrate it first. Right now I'm just essentially exploring. I don't have a particular goal. And it seems arbitrary. It just makes it harder. But the thing is that there might be some mathematical relationship with the new Taylor series and the knots that it represents. That would go into further research. So I'm going to do an example on the board so you don't feel so confused. And so for the trefoil knot, slightly better. The Alexander polynomial is x plus 1 over x minus 1. And then you replace it with t plus 1. These cancel. And so the infinite series for t1 over t plus 1 is that. I can tell you how to get there, but I don't have time. And so when you rewrite that, all you get is that. And so I just basically re-represented it. And again, it seems arbitrary, but it's just sort of exploration for other mathematicians to look into. So yeah, further research. And I think that you can play around with these Taylor series a lot. There are lots of different ways to represent them. And I think that mathematicians could potentially find a lot of mathematical relationships in these Taylor series and between the knots. And I think that's it. And I have some acknowledgements. I'd like to thank my mentor, Robert Raish. He did that lecture. He's a pretty cool guy. And he's really smart. I'd also like to thank Noble Energy. They sponsored my research and my stay at FSI. They're very helpful. And of course, I'd like to thank FSI and the University of Northern Colorado and all the people that helped out at FSI, all the mentors and advisors and stuff. And I think that's it.